Okay, so today will be our fourth and last part of neural networks. You're going to see your assignment later this week, and you're going to have from 2 to 3 weeks. I'll decide later when to, return the assignment. Next week we're going to be focused on convolutional neural networks, so CNNs. We're gonna stay there for like a couple of lectures. Then afterward, for the last few lectures, we're gonna discuss a few lectures about clustering methods, unsupervised learning, and bias variance. Some theoretical part in there. I try to make it as minimal as possible. And yeah, perhaps we're gonna end end of November, so in 4 weeks. If we manage to squeeze one more assignment after the second one, I'll let you know before. Otherwise, I have to wait these two assignments towards your overall assignment. And those guys who have been doing the projects and presentation, make sure to respect the due date. Okay. Any questions? All right. So last session we talked about backprop algorithm. So let's just recap it right here before we move on. So we mentioned that after each of the forward pass, we want to update the weights of our units, right? We want to update the weights at each iteration. So that iteration depends on one input set. So you pass the input, you reach to the end of the pipeline, you calculate the loss, and then you want to update based on the loss. Okay, so that's your input. You're gonna feed the network with a new X, and you've already arrived to the point that you have some W's. So these W's might be the first of the training, so like iteration number 1. So we're gonna discuss how we're gonna initialize those weights. But say you're in the middle of a training, and you're in iteration number 200. Okay, so you've already generated some weights, and then you pass another input. Then using a feed forward pass, you're going to have one output, right? You pass through all the layers from 1 up to capital L, and then you can compute the E of n, and then you find a partial E over partial W as a delta, right? This delta should be backprop backward through the network. So at first we're going to run the forward pass, we find the E and then the partial, and then using the gradient of the loss function and a pointwise to delta to the activation function we use. So it's a derivative of that. So that's a theta prime. That was your intermediate node S of L. So we're gonna update. We're gonna find the specific delta for each of the layers, right? The amount that needs to be updated, the differences. And then this is for one level, so that was one layer before the capital L, which was the last layer. What we're going to do is we have to just go into a loop and do an update for all of those previous layers one by one. So from L minus 1 up to the first layer, so we go backward, and at each layer we're going to find the proportion of this delta corresponding to that specific layer using a pointwise multiplication of that activation function prime of your S of L, and this matrix is just the amount of the weights, that current weight with the delta of the upcoming layer, right? So let me just write something. So this is coming from the. So you're at layer L. This is L plus 1, and this is L minus 1, right? This is coming from the next layer, delta of L plus 1. You want to use this and the weight for the Sj of L to find a delta here, right? And then you go one level backward again. This becomes the delta you found becomes the delta L plus 1 of your L minus 1 layer. And you carry on Wow, that was ugly. Yeah. So you carry on updating your weight backward in the network. Any questions from the last lecture? All right, so let's have a quick example of two-layer network. Let's see how those formulas are going to get translated into, okay? So say we have L equal to 2, so we have two layers. By doing a feed-forward pass, we're going to start from here. You pass the inputs, right? You compute each of those S's, which is the multiplication of your input and the weight, right? And then you activate those using the activation function theta. That would be the output of the first layer, right? And it's sort of for the node 1 and node 2, x11, x21, okay? And then you're going to have another set of weights here. Then you're going to reach up to here, which is the output layer, and then you activate the output layer, and that x2 is actually your xl, right? So this is equal to xl, which is the output. Then you compare the value you found from your xl and the actual y, so the real y, and you compute the E of n, right? With respect to the weights that you had already, these set of weights. So that's your E of n. Now we need to go backward and start updating these deltas, right? All those stuff in red, let me just clear this. So whatever you see in red are the backward stuff. Yeah, this is the first level of update, and using this we can update these two again. Okay. So in general, we need to compute the partial E with respect to W's. Okay, so I'm going to put the diagram on top right, so you have it as a reference. So what we're going to do here, for delta 1 of 2 of the layer 2, which is coincidentally our last layer, we need to compute the partial E over x1 of 2, which was the output of the network, right? That was the xl. L was 2, small network, so that would be the actual output, right? So using the chain rule that I talked about last session, so this is, we can expand this to partial E over the output xl multiply here partial x1 of 2 over s1 2, because this is the incoming node to the output, right? Here. So the error, the delta found at the end, the prediction error is dependent on the error here and whatever you're gonna find previously, right? So you're going backward. So the first element before this would be the node S12. Okay? So that's a chain rule. And this itself is equal to the activation function that you use in order to generate the output, this theta here, multiply this value would become theta prime of S1, 2. Okay? So that's for the first delta. Now that we find the first delta, so we know how we're going to update up to here, right? Now we step one backward, and then now we're going to update the rest of these weights. Okay? All right, so now we have one partial E over W11 of 2, this. So now, staying right here, looking back, you're going to see there are two incoming weights, right? Now I have to update both ways, going backward. First, I'm going to update the error that I have right now with respect to the portion that it was belonging to W11, and then on the other side, I have to update it with the W21 as well, right? So this is for this, and this one is for this, okay? Okay, now, so I'm arriving right here now. So I have two units, two nodes. So one is going to be delta 1 of layer 1. The other one would be delta 2 of layer 1, right? And for each of those, just like the previous delta here, so now we have to compute the partial E over partial S11, which is equal to, again, theta prime S11 multiply the delta 1 multiplied by its incoming input, right? The same goes for the delta 2, theta prime of, this is 2, make sure I update this, multiply delta 1 of 2, okay? So overall, we need to compute the partial E over each of those deltas for I and J, W I and J, where I and J are coming from the set of 1 and 2. We have two layers, two nodes, xi of 0 multiply delta J of that specific layer, okay?
On the first line, you have theta x1 minus y. Is that, I think, like previously, what it said?
It's just a loss function, right?
It's just the derivative of the loss function?
Yeah.
So it would be just 2 x minus y.
Yeah, I wasn't trying to just be super accurate here because it depends on your absolute error computation or square error computation. You're gonna have another way. So just make sure. So it's just a theta of your loss function, whatever it was. Okay. This is just a general way to compute.
Isn't it the derivative
Yeah, it should be the derivative. Yeah. Yeah. Say if you were using an absolute value, you don't have any square, right?
Yeah.
If you were using square, you would have two here. Yeah. Yeah. All right. So finally, we arrive to the point that for delta 1 of 1, we actually have to compute the W11 of the layer 1 multiplied of its delta plus W21 multiplied delta 2. Okay? For delta 1. Can anyone describe this? Why we have two terms to add for delta 1? And also for this.
Is there two inputs on the node?
Yes. So looking back, there are two nodes coming there. One node, you're looking at it, is W11, right? And it's corresponding to the delta 11. But the other node that is coming, you know the weights, it's 21, right? W21. But you don't know what's going to be the portion of the changes that you're going to update for on this side, right? That's why you have to multiply it by its own incoming delta. Also, with the assignment too, I'll make sure I post some sample questions about Backprop, so you get to know how the specific numbers are working here. But that's generally the way you need to compute that. And in the exam, normally we don't play around with big numbers and floating points and stuff. We make sure it's straightforward to compute. Okay? So, in the previous lectures, we've already been talking about the choice of questions.
Yeah, the previous slide. Could you explain that how did we come up with eta x1 minus y into eta dash s one?
This is it?
Yeah.
Yeah. So I was answering your friend's question as well. It depends on the type of the loss function we were using. If we were using a square loss function, we would have a 2 here because it's a derivative of that.
Yeah, so it shouldn't be eta dash like derivative of eta in this.
You remember the chain rule? We were talking about the derivative of the inside function multiply.
And the second part, that's eta dash s1. How did that be?
This is it.
Yeah.
It's because regarding the chain rule, if you want to get the update, if you want to compute using a chain rule, this value is equal to the one that is coming to there, right? It's a theta prime of the S1 to here.
So just to clarify, for the delta 1 on layer 0, there's the two components for it, that the weight for the input layer is going to have to change because it's being put to both of those two nodes.
Yeah.
So
Yeah.
there's an error associated.
So at each of those, let's say conjunctions, you need to make sure that how many edges are incoming, right? So you have to update both ways.
We can just use the normal, is it just the normal update rule with the weight plus the learning rate?
Yeah.
first equation on this slide.
These two?
Yeah. Is it weight 2 to 1 for the first line? The
2, 1.
Part, the 2 delta 2. Is it weight 2 to 1 or is it 1 2?
So at this node, it's 1, 1, which is doubly 1, 1 that comes here, and also the 2, 1.
What they're both weight 2 1s. Or the 2.
What is it?
First equation. Oh, on the right hand side. The second term. Second term should be W 1 2, I think.
This one?
In the first equation.
On the first equation, this, are you talking about this?
Second one. Second.
Oh wait, 2, 1.
Is this supposed to be 1 2? Or
Oh, I see. No, it should be 2, 1. 2, 1 comes here. No, 1, 2 comes there, here. Oh yeah, so this should be 1. Yeah, that's right. This should be 1, 2. This should be 1, 2, right? Yeah. Yeah, good catch. Yeah, because this point, look at this point, 1, 2 comes here, and 2, 2. Okay? This and this. For this point, this, this. Yeah, I'll update this as well. Let me just write it down somewhere. Okay. All right. I'll fix the slide later today, so you have the correct version. I was talking about the choice of the activation functions that normally we use in neural nets. You've already had a chance to know sigmoid function, which was e of e to the raise of s divided by 1 plus e of s, right? So it was slashing your weights from 0 to 1, where x equal to 0 pertain to half a point here. For the hyperbolic tangent, we were having e to the raise of s minus e minus s, and in the denominator we had e of over s plus e minus s. Okay, so we saw the advantages of hyperbolic tangent, and that the output of that will be around -1 to 1, for which 0 stays 0 at x equal to 0. Okay, and it was helping us to converge faster in neural nets. However, one of the more popular choices of designers for neural net is something else, which is called a Relu function, right? So that's a function of Relu. Yeah, I'll talk about it. Yeah, right now. So Relu stands for rectified linear unit, right? And a rectifier is just in circuits is a thing that just makes the flow to go one way, right? And if you take a look at the function, you see we are just slashing all of those weights on this side to 0, and on the rest we're gonna just leave it out. That's why the function of Relu is a max of 0 and s was the incoming signal. Okay. So for years it was the most popular activation function, right? Research has shown that it's going to bring a speed up of convergence up to 6x. It's very simple to compute. Its derivative is even simpler, and it avoids nonlinearity as well. However, using a Relu might have some downsides as well. Okay, let's see what are those. So first of all, as you can imagine, we are almost zeroing half of the weights in the output, right? So there's a phenomenon in deep neural network which is called dead neurons, right? And that's because of the use of Relu as an activation function in many of the modern state-of-the-art neural nets. So if Sj of L is smaller than 0, so the output would become 0, and then of course the derivative is also 0, right? So the weight do not get updated on the next iteration as well. When you update the weight, this is still 0. So in research, I've shown that around 40% of the neurons gradually die, or you're gonna have dead neurons throughout the network. Okay. So by updating, you're just wasting computation because it's gonna get again 0. So in order to solve that, in order to tackle that, researchers started to play around with the Relu function, and they saw how they're going to change this behavior while they keep the computation as simple as possible. Okay, so they come up with many variants of Relu. We're going to talk about 2 of them today. So the first one is a leaky Relu, and a second one is a parametric Relu. Both of them are actually doing the same thing, but one is has a parameter alpha which we can cross-validate or play it as a hyperparameter, right? The other one is it's a sort of fixed hyperparameter, normally around 0.1, so that alpha, right? For those weights who are smaller than 0, we don't make it completely 0. We just multiply alpha to that. It's a very small number, okay? So leaky Relu allows a small positive gradient, right, when the unit is not active. And as I mentioned, for the parametric Relu, we can use our training data to cross-validate and come up with the, say, the best found hyperparameter for that alpha, okay, for that specific network. If you want to see an example of leaky Relu or parametric Relu, this is sort of looks like this, right? If you have that parameter, if you set it to 0, 1 of x, you're going to have a very, very mild slope here, right? Which is not 0. And for parametric Relu, you just have to, find that specific alpha or a for yourself. So the advantages are you avoid dead neurons, right? And the dying gradients. And it has found that it's going to speed up the training process as well. All right. So now let's talk about input processing of a neural net. We've talked about the feed-forward path, the backward path, the type of activation functions we need to use. Let's see how we're going to play around with the processing or pre-processing of the input when we are trying to train such a model, right? So that's your big data set of D, contains all of your supervised data, right? You have the labels and those vector of x's from x1 up to xn. So in statistics, it's pretty easy to compute the mean, right? We call it mu. So that's a mu, vector of mu. which is simply the summation of all those x's divided by their numbers, the number of those. Okay, just like that, having a sample data set of G, you can compute the sample variance. This is something like this. Okay. From J from 1 up to D, which is a distance between each of your points from the mu you found from the mean, and you just make it square and divide it by n, and then you have one square root on top. Okay. So, just like any machine learning model in neural nets, also it is better to normalize your data set because you're pre-processing your data. They might come from different sources, sensors or images or whatever. So if you are trying to train a model, normally it is advised to normalize your data set. So by normalization, you need to find the mean and the variance. And there are so many different ways to normalize it. You're going to divide it by the variance, or there are countless different other approaches to normalize your data set, right? So this is one way to pre-process your data. The other one is, so yeah, the one that I mentioned is you subtract the mean from your x's, and then you divide it by your variance, okay?
What are we trying to do with this?
What is it?
What's the point of it?
So say you have a CSV file. I'll just write it here. So you have 0.5, 1200. On the first column, the second column has 15 million, and then 1. Okay? So you have two columns, and you have two features. Right? So if you want to process this data, because the differences are very large, right? You have 0.4 and then you have 15 million on the other side.
Yeah.
It's going to make your training very noisy, right? And the accuracy might drop by processing this data. So normally you have to do one step before this. We call it the pre-processing step, right? You normalize this data. So the output of the normalization might make sense. I mean, there are some normalization technique that makes the output from 0 to 1 or from -1 to +1, depending on the paradigm. Or sometimes you are having two different sources of incoming data, say from two different sensors, and each of them have their own scale, so you cannot compare these two and add them together as one huge data set. You have to normalize them each, and perhaps after that you normalize the superset ones together.
What was J again?
J is all your numbers. So yeah, perhaps I should have used. So these are the D from your features.
Oh,
In this method, we normalize it based on each column, right? Based on each feature. I mean, there are multiple ways. They treat the whole as one. Yeah. So it's just experimental setup. You can play around with different methods. All right. So another way to make your model more robust, especially when you are dealing with lack of data to train, is another process for preprocessing called data augmentation. Okay. So you apply a function of f, and that function could be anything, like any geometric function: rotation, flip, scaling, cropping, right? Say you are trying to train a model to distinguish different breeds of cats or cats versus dogs, and all of your images are just the cats that are looking on this side, right? So For sure, if you train your model using all the cats that are looking this way, if a cats come lying on the left side or the other way around, you might not just understand how to classify it, okay? So using data augmentation, you can define multiple functions to randomly apply different geometric functions on your original file and generate these 6 out of that, right? You flip it around, you scale it, you change it, rotate it, and by this one you can enlarge your data set here by 6x, for instance. And then you train on those. You make your model to see more of the examples. I mean, this has its own downside. It's going to make your model a little bit noisy, but there are so many different things you can apply after that to compensate the loss. Yeah. Okay. As an example, in TensorFlow, we have, if you take a look at the TensorFlow GitHub, this file for preprocessing inception model. So inception is one of the recent state-of-the-art CNN models, a convolutional neural network. So there are some preprocessing function for training that you can play around and distort images, right? Just like what we had in the previous slide. You play around with the width and the bounding boxes. The B box is the bounding box. And change the color scheme, random cropping, and so on and so forth. Right? All right, so that was for the pre-processing. I'm just gonna, I'm trying to just put out as much as information as I can. But as you know, there are so many different things that you can, if you just focus on pre-processing, we can have 5 lectures of that. I just wanted you guys to at least know one full, understanding of all of those parameters that are involved in training a neural net. That's why I'm just trying to just go for the next one as well. So after pre-processing, there is another issue with training a neural net, and that is how we're going to initialize our W's at first iteration, right? We know how to update those, but how are we going to start with the weights? So one simple method is just you assign small random numbers, right? So, and the numbers are coming from a normal distribution, right? So you assign all of your W's of I and j of layer L, could be any layer, from a normal distribution from 0 and 10 to the minus 2, okay? So the issue with randomizing your initialization is you're going to have a vanishing gradient in the neural net. The more you go forward, the more you iterate more and more after 100 iterations, 200, 500, and 1,000, you see that because the initialization was very, very small, your updates, which are the derivatives of those, will become your gradients to go closer and closer to 0. And that phenomenon is called vanishing gradient. So, and this will be an issue down the road. And at some point, your weights are gonna get so close to 0 that virtually you don't have any updates at all. Okay. All right. So let's see how we're gonna change this thing. Can we update it another way? So there was a researcher in University of Montreal called, his first name was Javier. That's the paper that I mentioned. So he was working with Yoshua Bengio, so the famous guy at Montreal. So these two provided this paper, so you can have a look at the paper. And the way they initialize the weights was later known as Javier initialization. Okay, so it tries to make the variance, right, of the output of a layer to be equal to the variance of the inputs. Okay. So for each of those i's from 1 up to n, you have this variance of the weights equal to the variance of the g's. And this idea turned out to be very useful, right, in practice. And naturally, you can see that this way of initialization depend on the layer activation function. On that paper, they were using, I believe, sigmoid as their activation function. So your weights are coming from a normal distribution from 0 and 1 over n. Okay. And n is the number of nodes in layer L that connected to node J. So for any node in the middle, so S of J of L would be the sum of all the x's from I up to n, x I L minus 1 multiply their corresponding weight, right? So when you play around with the deep learning frameworks, Caffe, TensorFlow, and else, so you can just define it as another argument when you try to initialize it. You can pass it as an argument. All of them have been implementing this initialization already in their framework. So if you compute this, the variance of that S of J of L is equal to 1 over n of the summation of the xi's, and this is almost equal to 1, right? Now if you combine this for the S of J to update the W's, we're going to have all the W's as almost around 2 over n, and thus it results in half of the neurons being inactive. And we call the variance of the W, I, and J unity, which is equal to 1. And it helps us actually to decrease the chance to be being struck in saturated regions when we are using hyperbolic tangent as activation function. Yeah. So when you design a neural net, depending on the choice of your activation function and initialization, you need to play around and tune those components to use in order to optimize your training process. Okay, and one last thing is the dropout, which was proposed by Jeffrey Hinton and his collaborators in 2014. So that's a paper. It has a very simple idea. You might have heard of the word dropout. And we just stochastically drop in hidden units. And normally that probability is 50%. You can play around with the hyperparameter, but the default is 50%. So at each of the training stages, we randomly select half of the neurons and make them to 0, right? We drop them out of the equation when we are doing the feed forward. So when you have such a model like this, after applying dropout on this layer, so you're gonna have something like this. If you drop these 2 out, right? This is not 50% in this case, but just for an example, we drop these 2 out of all of these here, right? So the output would be this. And this very simple task turned out to be very useful in order to avoid overfitting, right? because at each point you are dropping some information out of your neural net, right? And you avoid and you sort of hinder your neural net to learn too much about the specific incoming example, right? We don't want that to overfit with respect to one input, right? We want to make it as random as possible, so the noise are. This is sort of inserting some sort of noise into your model to avoid overfitting. Okay. In general, if you do that, you might expect to have a longer convergence rate, but overall, it's going to help you to converge faster at the end, right? And for testing, when we want to test on a new data set, we use the entire network, but scale weights by a factor of 1 minus p, right? Assume that was half a point, so it's going to be half. And the advantages, as I mentioned, they do not rely on strong activation. It's very simple to implement, and it helps avoid overfitting, okay? Any questions? Okay, so expect your assignment to be posted in a few days, and then next week we're going to start CNNs. Have a good day, guys.